My guest today is Melanie Moses, a professor of computer science at the University of New Mexico, external faculty at the Santa Fe Institute, and chair of the New Mexico AI Consortium. Melanie's work spans a wide range of disciplines, all unified by her deep understanding of complexity theory. In our conversation, Melanie and I explore how scaling theory reveals surprising patterns across nature, technology, and society. We discuss what centralized systems like ant colonies can teach us about building more robust AI, and what the immune system tells us about information networks. We also delve into the costs of building scalable infrastructure and why we might need new approaches to governance that can scale with our global challenges. Finally, we explore whether there could ever be a universal scaling law and what young researchers should know about pursuing interdisciplinary paths. I hope you enjoy our discussion. Melanie, thank you so very much for coming on the podcast. I've been trying to get you on a podcast for quite some time. So today is finally the day, which is very exciting for me. Before we start with a deep exploration of your work and how it relates to scaling theory, I thought I would start with a fun question that I've never asked before on the podcast. If you were given $1 billion grant to study scaling across systems, whether we have in mind biological, computational, or societal systems, what would you build or test?
Fantastic question. And let me just start by saying thank you for having me and being patient for me to have this conversation with you. I'm really looking forward to it. And thanks for that great question. It's certainly fun to imagine what one might do with $1 billion, particularly in this funding climate where coming across scientific funding for grand ideas is a little more difficult than it used to be. But I would have to say that within resources like that, I would want to tackle what I feel is a real imminent threat to human society. And as I think about that, I think our biggest problems are probably around self-governance. The way we, as our 8 billion humans on this planet, have built systems to govern the ways we interact with each other and the earth. And so I think one of the things that's becoming apparent is that scalable trust is really difficult. So building systems where people can trust that other people are following a set of rules that have been laid out and that those rules are actually leading to a world that's a better place for everyone. And how do we build scalable institutions in your domain, scalable legal systems that foster collaborative progress, that are not overburdened with a kind of bureaucracy that many people hate, myself included. No one likes the hard work that you have to do in the systems we have right now to make sure people are following rules. I think there's room for progress there. And I think scaling theory might point to ways that we can interact, perhaps in somewhat less centralized ways. The American system actually has some lessons there with our federalism that allows states to experiment and local governments to experiment, a framework that's set up to be modified. So we haven't done a terrible job with this. And in fact, if we look across biological systems, like no other organism has come even close. It's in some ways astounding how we have built systems to cooperate with each other. On the other hand, we've also created problems at a scale that the world hasn't seen before. I do think we need new approaches to govern how we interact, to tackle things like our climate problem, scalable democracy, right? What is a democratic institution that could really lead to a more peaceful and ecologically sustainable world? I think I would focus on that. And I have to say, I recently, just this last weekend, I was on a flight. We all spend probably too much time in airplanes, speaking of the climate challenge. Sometimes I get on an airplane and I'm absolutely astounded. Hundreds of people get in this steel aluminum thing and trust that it's going to stay up in the sky. You've got to trust the pilot and the FAA controllers and the engineers who built the plane and your fellow passengers. And the vast majority of the time, this works out just fine. Even though there's some fallibility in all of those components, we've built systems to do that. But when we look at our approaches to mitigating climate disasters and our proliferation of plastic on the planet, we haven't seemed to have built systems that are so trustworthy and so good at the job of fixing a specified problem. So that's where I'd invest the billion.
Let me ask a follow-up question on that. So if you were to draft the grant proposal, right? So before you actually got that billion,
Yes.
is your intuition telling you that in order to create trust and to scale it, you would need to combine computational methods with legal governance and look at how what's happening in the biological world, or would you favor maybe one of those approaches?
Yeah.
It's just to be clear.
Yes, I would probably spend a little more time. I would certainly need to spend a little more time thinking about that. But I do think that it is in this sort of intersection of computation and law, right? Where computation does give us specificity and, in some senses, trustworthiness, right? So, for example, computational hardware, right? It does what you tell it to do to first order absolutely all of the time. The legal code is necessarily more fuzzy than that. There's room for interpretation as well, there should be, but some sort of a mix of code that can guarantee that this is a result and the legal code, right, which is much more adaptable and open to interpretation. So I would look in that space. And I think the piece that I would maybe bring in from biology is the idea of natural selection and adaptation, which again, I think does exist in the legal code, figuring out how to make that even more precisely a goal, right? Like we talk about, for example, experiments in the States with new legal frameworks or new laws. We have some of that going on right now with AI regulation, for example. But we don't necessarily have a system that really looks at what is going on at all of these states and where should we actually elevate a particular approach that has been successful and combine approaches that have been successful at different states. I think there's room there to really energize that kind of an evolutionary process where we actually learn, where we learn from our mistakes and our successes a little more directly and intentionally.
Yeah. So that's a perfect segue to part one of our conversation, in which I want basically to jump from one field to the other, because this is what you've done in your literature, observing scaling everywhere and looking at nature. What we see is that size often correlates with lifespan, metabolism, and behaviors. Now, my question is this: do you think these biological scaling patterns have analogs in the life cycles of technologies and institutions, such as we just discussed?
Yeah, absolutely. Many of my colleagues at the Santa Fe Institute have studied exactly this question, right? Taking what we observed in nature, in biological organisms, largely is where scaling theory has applied, and said, do we see the same thing in collections of humans, for example, in firms and cities? Over and over, we see these patterns. There are scaling patterns, although they're often different in social systems than they are in biological systems. Just this, I think the most powerful piece of this is the framework, the idea that you should look at how variables consistently change with things as they change in size over orders of magnitude, not when they get 50% bigger or double in size, but when they're 100, 1,000, a million times larger. And we can do this because of our ability to cooperate, right? We have built institutions of various sorts and societal cities and things like that, that have orders of magnitude and variation. And certainly we see that some of the patterns that we saw in biology persist. But for example, in cities, if you look at infrastructure, which has a nice direct analogy to, say, a cardiovascular system, which is the infrastructure for your metabolism as an animal, there we see sublinear scaling, right? It takes more time to push resources through a bigger physical system. But we look at information systems, things like patents, negative interactions like crime, those sorts of things scale superlinearly. As you put more individuals together, you have more potential for interaction on a per capita basis instead of less. And early on in the scaling literature, those superlinear things were also seen, which suggested there are certain things related in general to information and interaction that actually increase as you add more and more individuals.
Yeah, you just mentioned cities. that leads me to ask about your work about urban roads, networks, and the growth of cities. In your work, you explore how you may find similarities between the growth, the scaling of the cities, and the ones of biological organisms. So again, what scaling patterns similar to biological ones have you identified when it comes to urban infrastructures?
So we looked at road networks, and that was actually one of the first projects that I engaged in as a young professor with my postdoc, Horacio Samaniego, many years ago at this point. And we were interested in road networks specifically, and we were interested in it because it was such an obvious analogy. We talk about road networks as veins and arteries of cities sometimes. And there were data available to ask questions about both the physical infrastructure. So essentially how much pavement do you need, right? How many lane miles do you observe in cities of different size? And then at the same time, we could look at how many miles are driven per capita in at least a small number of cities. And we looked at US data that was available at the time. And what we found, and we had a hypothesis that if roads were serving the central downtown area of a city that you consider as the heart of the city, and we had the same pattern we'd see in biology, we would expect, instead of the 3/4 power scaling that we see in biology, these are largely 2D systems, we'd expect this sort of 2/3 scaling law, that the sort of volume of traffic that could be delivered by the roads would follow this 2/3 law. But we also hypothesized maybe cities aren't really designed like that, right? Especially you think of a city like Los Angeles, right? It's very decentralized. There are little hubs all over the place. There's not just one downtown where everyone doesn't commute to the same location. And we said what amount of pavement you would need to serve the city, what would it look like if it were purely centralized versus purely decentralized. And what we found is that it was somewhere in the middle. Almost exactly in the middle. In fact, there's some aspect of cities that's centralized. People do, in fact, downtown is downtown for a reason. It is called the heart of the city for a reason. But there are also lots of smaller trips, and people adapt to this. And now we even have movements, right? These sort of 15-minute cities and things like, let's make it so that people don't have to travel so far to get to the services they need or their jobs or their schools. What was most interesting to us when we did this is that when we looked at miles driven, they appeared to be more centralized than the building of the roads. In other words, road capacity didn't really keep up with the nature of the additional miles that people drive when they're in a large city, and they still very often have to travel across town or go downtown. So we thought of this as an explanation for why these large cities have such traffic problems, right? It's a failure to scale the infrastructure with the real way that people move through cities.
So you've mentioned Los Angeles is maybe one example of a quote unquote decentralized city to some extent,
Right.
but then you have other cities such as Santa Fe, New Mexico, or Amsterdam. And yet, despite what may appear to be very different, you do find that there are scaling laws with, of course, some deviation here and there, but there is a pattern.
Yeah, you still see a pattern. And it's important. I think this happens in many social systems. There's always deviation in these scaling so-called laws, right? It's a pattern, but there are cities that have more and less centralization and things like that. In that particular work, we saw more deviation than we would see in a typical biological scaling relationship. There's a lot of room. Perhaps there's not been sort of pressure to optimize, but maybe that's even the wrong way to think about it. I think that in these human systems, there's a lot going on. There might be geographic reasons why some cities might make different choices than others, and that might be ideal. This is, again, one of those sort of humans maybe didn't make the best decisions about where to build roads and how to invest in roads, where there are just so many other constraints that sort of drive deviations there. So yes, patterns. You could learn about Santa Fe and make some predictions about what you might expect in Los Angeles from these patterns, but it's not going to be a hard and fast, firm rule, right? Things might be 2, 3, 4 times different than your predictions.
Yeah. And I could imagine indeed how you may, as a mayor, actually run on the idea that you're going to lower taxes at the city level, in exchange for which you will get less infrastructure. But still, you do see superlinear scaling. Looking at another system where you do see also superlinear scaling is the one of human networks, such as social media or organizational structures, where you see that the flow of information is increasing. The larger the network, the more the flow of information is increasing. So can you tell us about your work in the space?
Yeah, a lot of what we looked at and thought about and have over the years is thinking about computation broadly. So not necessarily social media, but if we look at the lower levels of, or even the lowest level, how are computer chips designed, right? That I think has some lessons more broadly about how information scales. So in the cities examples and the social systems, social media included, what we tend to see is more decentralization. And we see this trend. We're not all getting our news from one or two or three centralized sources. We are exchanging information directly. And our work suggests this actually makes sense for any information system, largely, I think, for two reasons. One is that information can be very cheaply copied. It's not free, but it's extremely cheap to copy a bit in a computational system. And so if you want information to percolate through an entire system, you don't really need to send it from one place and move it through something like a cardiovascular network, where if you've got 1,000 individuals, you don't have to make 1,000 copies of the information at the center and move it through the entire network. You can make copies along the way. So you can send, say, 2 bits or 4 bits in 2 or 4 directions, and then make copies as you go. Additionally, you don't have to even have that centralized source, right? You can say, oh, anyone has some probability of communicating with any other individual. We looked at how you might make that a scalable system that requires less communication channel. In fact, the way that hardware is designed, because it needs to be energy efficient, you communicate less often with things that are physically further apart. And so that leads to something that's indefinitely scalable. What that means is then you can have isolated parts of a network potentially, right, where communication is just local. And I think that's the trend that we see in information networks and social media, right? And we talk about them as bubbles. But in some sense, in terms of communicating, it's very efficient, right? You form this little bubble and there's exchange of ideas in these bubbles. And if we want to push back against information bubbles, which maybe have societally negative consequences, you have to recognize there is maybe a natural tendency, right, for individuals to want to communicate locally. And it's easy to think about that because there are 6 billion people on the internet. We can't communicate with all of them. There may be interesting things that those 6 billion people have to say to us, but we can't process it. And to me, there's maybe this kind of fundamental reason why we need to create, once we suddenly have the ability to communicate with everyone, we have to create some sort of filter in order to minimize that flow of information, right? It's too much already, right? Imagine if we didn't have these information bubbles, if everyone actually knew everything that everyone was saying, that it gives me a headache just to think about it, right?
And that filter may be a technical one where you get curated and personalized information, may also be a legal one where you may want to say this kind of information we don't want on those platforms. It may be copyright, which also is a good way to reduce the sharing of information by preventing it or making it illegal. So taking a step back, and we already explored quite a few fields already, biology, the making of cities, the law, others. It feels that you are the right person to ask the following question. What is the most underappreciated insight in scaling theory today?
I think there is still, outside of scale circles and complexity, outside of the complexity bubble, I think scaling theory hasn't necessarily percolated into the sort of popular consciousness, right? So people don't necessarily understand the basics. And the idea that things really change systematically over very large scales. So that's people within the bubble understand that, right? That there are these systematic changes and there are particular rules that one can understand that lead to particular mathematical representations of how things change with scale. I think that basic framework is not yet appreciated as widely as it should be. Within the bubble, I think there is a growing understanding of the importance of whether the system is centralized or decentralized. In these city systems, information systems, including the immune system, which we might talk a little bit about, that I've studied a lot, tendency to decentralize. So everything doesn't have to go through the central heart, the central lung, but in the lymph nodes of the immune system, for example, things are processed in a distributed way. So I think there's a growing understanding that decentralization fundamentally changes scaling laws. A decentralized process will essentially allow things to scale up, not necessarily more efficiently, but scale up and allow more interaction because it has the ability to have local interaction. Everything doesn't have to go through some central node. I also think there is something that I think should be studied more is just the cost of the infrastructure. Even a decentralized infrastructure costs something, right? To build, say, a decentralized network of lymph nodes costs something. So these scaling laws don't come for free. They require some organizational system. Maybe one example of that is, so we have done work in swarm robotics, where we had these swarms of robots and they would go around and search for something and mimicking what we characterized from ant foraging behavior. And we were actually pretty successful in getting groups of robots to cooperate to find resources in a landscape and bring them back to some central place. But when we tried to scale up to dozens, hundreds, thousands of robots, which we could only do in simulation, we would see real bottlenecks without having some sort of infrastructure to facilitate the movement of robots over large spaces. So in that case, we built in simulation a fractal branching network, completely mimicking the theory, the biological theory, the West, Brown, and Enquist and original theory of how one should construct a network like that, but allowing individual robots to change speed, changing the size of the robots that would carry. We'd have big giant trucks going through a central corridor. So we could mathematically predict what would you need to do to overcome scaling limits. And so we could build that infrastructure, and then we would have a far more efficient system. You could have robots behaving like ants in a decentralized, uncoordinated way out in the leaves. But when they had to move things, they would be constrained to this kind of a centralized scaling network. So that had huge benefits, but it also has a cost. You have to build the roadway. You have to invest in big trucks. I think that piece of scaling theory would be worth studying a bit more. What is the cost of building the system that allows a scalable solution? That gets back maybe to your taxes point, right? How much tax do you have to charge in a larger city in order to build the kind of infrastructure that you need to make the city work?
And for people outside the bubble, what would be an efficient way of making scaling theory well known?
I don't know. I might leave that to the marketing folks. How do you get this message out? But I think that the key is to connect this to the things people understand intuitively. Yeah. Some of it's very visually obvious. People see trees all the time, right? We see this fractal branching structure. There's a beauty to it. And I think maybe a lot of it is just having people connect to what they see in trees and river networks, and then to realize, oh, this is also something that's going on when I'm driving to work. In terms of, there's mathematical approaches that you could teach people. You could teach people about logarithms and how you should look at things multiplicatively and that sort of thing. But I think in order for people to really understand it and relate to it, maybe it's really just more of, hey, look at this, the world around you and the way that humans have mimicked the building of these kinds of systems. Yeah. The legal community could perhaps do the same. Maybe there is some scaling there.
Through beauty, in a sense. There is one example that comes to mind in the book of Jeff West, when he explains that if you have a kid of, let's say, 10 kilos or 20, then you do not simply double the size of medication or the dosage that you give to the kids. Right. There is also a website that I use a lot for cooking, Marmito. I think it's a very French website, but it's pretty convenient in the sense that you could say, I want to cook that dish for 4 person or 6 or 8. And then if you go from 4 to 8, the quantity of each of the ingredients will simply double. And I'm always like, no, this is not how it works.
Scaling laws. And when you bake a cake, the surface area to volume of the cake changes. And so the ingredients are going to have a different relationship to the outside world versus what's happening inside, for example. So that's recipe. Everyone loves recipes. So maybe that is a great way to.
Let me ask the final question for this first part of the conversation. Do you think we will ever find a universal scaling law that explains the growth of everything And maybe, perhaps even more fundamentally, should we look for such a universal scaling law?
No, I don't think it exists, but yes, I think we should look for it. I think that the framework maybe is universal, like the concept of let's look at things and let's look at different variables that you might call size, and let's look at how things change systematically. But I think just like with the moving of energy through a network scales differently than the moving of information through a network, I think there are contingencies for each of these quantities that you might look at. Maybe energy and information, maybe those are the only two we need to consider. But I think that looking for the one true law is a worthwhile exercise because it forces you to look for commonalities. But I don't necessarily think that we will find this sort of one theory of everything. I think we will find a collection of theories that explain many different things, and we need different tweaks on the theory. But the goal of looking for them, I think, is really important, right? It's not that we're looking for them because they're there. We're looking for them because it's an approach that lets us find regularities in the world that we might not have otherwise seen.
So you're saying we won't find them because that law does not exist, or because of our limited capacities?
I think that one law, maybe, I don't know, I'm agnostic on the question, but I think there's reason to believe it might not exist, that understanding how things move through systems requires some understanding of contingency. And if your universal law ends up looking a legal book, right, that yes, this is the universal law and it's 100,000 pages long, then it's not very helpful. So is there one simple rule that explains how ant colonies search and how blood moves through your vessels and how all of these other pieces of scaling and how cities are organized? I think it's not quite that simple. I think it's a way of looking at the world that has these different components that you really have to start to consider to actually explain things that are useful. And so this is different than saying, I think a lot of people in the scaling community will say, oh, biologists look at the world and say, oh, nature is a many splendored thing, right? They're just all of these different things. And it's like the way that the theory of evolution, in some sense, explains all of this diversity. But the specifics of how any particular thing works is very contingent. And so I think scaling law is of that nature. It's a really central theory. It's an important theory, but it doesn't explain everything on its own. And I don't think that it will.
So let's take that for granted, at least for now. Still, we have scaling laws that are way more specific, and we've covered a couple of them. You have identified a couple of them in your work. So I want to move now to part 2 of our conversation, in which we take those scaling laws and what we've learned about it and try to see if we can use them to build scale and more robust networks. So my first question would be this. When it comes to biological systems like ant colonies, the immune system that indeed you studied in depth, what can that teach when it comes to computation at scale? And what I have in mind more specifically is whether principles such as decentralization or redundancy can teach us something when it comes to scaling our ability to compute the world.
So let's see. I think it teaches us many things. One of the things we came to when studying ant colonies and immune systems, in both of these cases, we were studying how do these systems search, right? There's no central controller. The queen ant is not directing things. There's no even concept of the queen immune cell. These are systems where there are hundreds, thousands, millions, even trillions of agents, in the case of the immune system, that are spreading out over some space looking for something. Ants might be looking for food. Immune cells are looking for pathogens. And they have some commonalities, actually. So this goes back to, is there a universal law? Not exactly, but there are some real commonalities in the way that immune systems and ant colonies work and search for things. And there's some lessons there, I think, in how we might build more decentralized systems. So some of those lessons include, it's very well understood in ant colonies that ants will, for example, lay a pheromone trail. So when one individual is successful, it might lay a chemical trail from, say, the location of food back to a nest. And that trail can be reinforced by other ants that follow that, lay their own chemical trail if they are successful, therefore reinforcing it and making other ants more likely to go to this location. And then they leverage the natural evaporation of chemicals, right, on a landscape, so that if the food disappears and the reinforcement stops, then the trail disappears. And so this is an amazing way to make a map of the landscape and where food has been found to direct the other ants. And in this case, there's not any centralized control that's needed. There is both a decentralized behavior of individuals responding to their environment, and also a bit of a centralized location where every ant that comes up out of the nest is going to see a signal or a gradient of signals in different directions to make a choice. So there is some interplay of centralization and decentralization in that system. I think that's an important lesson. So in the immune system, I mentioned lymph nodes, which are decentralized locations that are spread throughout the body. We've done a lot of looking at how lymph nodes, the numbers and sizes of lymph nodes scale with the size of the animal. In that case, you could think of each lymph node as its own little nest, where the search process, where cells like T cells of the immune system will be searching for indications of pathogens and trying to do this process of identifying the right T cell to find the pathogen. There are chemical signals called chemokines and cytokines that are used to produce feedbacks to tell the immune system, this is the location where perhaps there's an infection, or more immune cells are needed. We ramp up chemical signaling that says more immune cells are needed here, and it interacts with the blood cells so that immune cells exit out of the circulatory system in the right place. This chemical communication that's reinforced with positive feedback is something we see in both of these systems. But we also see a tremendous amount of randomness. Some ants, it's actually quite frustrating if you spend time out in the desert following ants around, that many of the ants will come up out of the nest. There's an excellent path to a giant pile of food that you've provided for these ants to run your experiments. And then large numbers of ants will just ignore that and wander off in another direction. And that is really indicating to me that we've done a lot of modeling to show that kind of behavior is actually adaptive. That exploration for the next pile of food, while others are exploiting an existing pile of food, is really important to be able to find food in an uncertain world, right? We don't want everybody following the chemical trail. And the immune system has a lot of that as well, which I think has frustrated immunologists to understand, like, why is there so much randomness in this system? But some of that we think is also adaptive. And so that's a lesson that we can take in our human systems. I like to think about that in the production of science, right? We build departments, we build sort of these trails that say, hey, there is interesting knowledge here. You can build upon the work of others in this direction. And that's fantastic. That's created many of the scientific advances that we all love and appreciate. But it leaves lots of unexplored territory. And so I think the question is, how do we incentivize people to go off in other directions? Some of that is interdisciplinary. Some of that is just pursuing ideas that maybe weren't the popular ideas in the past, but there may be some nugget of truth there that if you follow that, you might find something useful. I think humans are a little too eager to follow the crowd and build upon the success of others, and not as rewarded for going out and exploring new things, many of which may fail.
Yeah. So this may be also a problem, and we discussed that with James Evans on a former episode of the podcast, of the use of AI, right? Because it may be easier to follow the path of others, and maybe you will be less tempted to explore. And actually, just today, I read a paper published in Nature called The Pivot Penalty in Research. And it shows that the more you go away from your core research, the less you are being rewarded for it, because the less citations, the less likely to get patents, because you are not seen as an expert in the field. So maybe we need to work on that a little bit. But coming back to AI, it seems that there is a complex relationship between hardware and software that could use for more robust network and address some of the issues that we've seen in hardware, where we see supply issues, and in software where you see AI, discrimination and biases and so on and so forth. I'm not sure if we can solve any of those issues just doing one layer at a time. So what is your work telling us when it comes to that relationship between hardware and software, between the physical world and the digital one?
So first, on your comment about AI having the potential to just narrow our focus on particular, build on past successes, certainly there is that possibility. But I actually think, whether our current AI does this or not, I don't know. But I think there's tremendous potential for AI to do that exploration, right? To set off a group of AI agents, each of which have a different sort of motivation, a different direction they might explore, even using the current technology, which is somewhat limited in that it's building on things that we already know just a tremendous amount, right? So focusing AI's agents on look for problems that once seemed promising, but then something took off, right? Some particular approach or methodology became the standard. Look at the 17 or 17,000 other things, right, that were explored that could have become the standard. What if you built on those for a while? Go in those directions. So I don't think there's anything inherent, even in the current AI, that would keep us from incentivizing AI to explore new areas. And I think the lesson we might learn from something like ant colonies is that we want to invest. There are lots of theories about in natural selection, by what proportion do you invest in success, right? Do you invest exponentially in the most successful approach? That's like following the pheromone trail. Maybe we need to specifically invest in things, right? Put your money in agents that are exploring unsuccessful regions for a little longer than we've done in the past. I actually think that AI, in that sense, the limitation there is the way scientists are incentivized, not the way that AI is built. To your question about hardware, and I think you're asking there, do we want some other architectures, not just these neural network architectures? Certainly architectural advances, things like transformers, right? And even convolutional neural networks, these lessons that we've taken from increased biological understanding of how actual neural net circuits in brains work, they've been transformative, right? They've actually made enormous differences in our ability to classify things and find patterns and predict things. But certainly there are more lessons to be learned by what's often called neuromorphic computing, actually thinking about building hardware that mimics the human brain or animal brains. I think that a lot of the advances will be in how do we network different neural networks together. I think we tend to attribute too much in the incredible human intelligence that we have to the neural networks in our brains and not the interactions that we have among us. We have different kinds of networks that connect up these brains to solve problems. Scientific advancement very rarely happens because someone has an incredibly smart brain. You can look at Einstein and a few examples of people who have really advanced the field, but most of it progresses because we find effective ways to collaborate and build on past knowledge. And I think that might be the piece where AI potentially, there's a lot of low-hanging fruit, right? So everyone's talking about agents now. I actually studied agents as an undergraduate. I made up a concentration in my major that was called agents. And I used to keep that off my CV. And now I say, I've been studying agents for 30 years. This idea of how do you connect up these agents that have, I don't know, what we might call some kind of unreliable and flawed intelligence that we have in AI. We also have unreliable and flawed intelligence in our human minds, and connecting them up in a system like the scientific method, right, that is designed to find the flaws and seek truth by constant questioning among different agents. I think that's where the money is. Maybe I would put some of my $1 billion into that, mimicking, you talked with James Evans, right, mimicking social systems and experimenting with them. What kinds of systems allow this collection of agents to come to make new discoveries that are either novel or more aligned with the truth? You could think about different ways to experiment with that.
So that will be, in a sense, scaling intelligence by combining those two different ways of approaching knowledge and information. What about the other side of the coin, where you will have systems that will collapse, right? Or at least be on the downslope, whether it's a foundation model that is being abandoned, but still used by some people, or a social media powered by AI that is also abandoned, but some people are still on it. Is there something we can also learn from nature? And I guess more specifically, should we and can we design the system to fail like nature, where it's more graceful and incremental without a total collapse? Or should we keep that separate?
So certainly, of course, we should learn from nature. I study bio-inspired computing because I think there's a tremendous amount to learn from nature. We also don't want to make the mistake of assuming that things that happen in nature are ideal. They're not always ideal. When you look at ant colonies, one of the ways that ant colonies are so effective is that all the ants are willing to die for their sisters in the colony, right? And that's not something I would advocate for human society. I don't think we want to build a society where what happens is, well, all individuals are willing to sacrifice themselves for the good of the whole, and individuals are regularly sacrificed, right, for the benefit of the whole. That's not necessarily the model that I think any of us want or that would be ideal. And you do even see catastrophic failures in the immune system. There are lots of examples of this. Much of the immune response to COVID is an overreaction. And things like cytokine storms, where these positive feedbacks that say, there's a terrible novel infection here. You need to build more of these, create more of these T cells, bring them here. And these T cells are destroying your cells in an effort to kill the pathogen. And so you get this cycle of increased chemical signaling and increased attraction of damaging immune cells, right? And that can itself kill you. So you don't necessarily have only graceful failure in these natural systems. That doesn't mean we can't learn from them. They are, right? The immune system probably is the most exquisite example of a system that can learn over your lifetime. So it has been described as evolution reinventing itself inside your body to evolve new receptors that will recognize new pathogens over your lifetime. And that's just stunningly, just a beautiful solution to the problem of having to learn. So there are lessons there, but I think we just have to remember that these systems are not necessarily the perfect model of how we want to build, say, a human society or something of that nature.
Yeah.
There is one other lesson, though, I think is important. And I've just been thinking a bit about this. One of the retorts to this, one of the problems that's been pointed out with these large language models, which have many problems. They're also amazing, right? It's really fun to say, write a Shakespeare poem and write it in the form of a Simpsons episode or whatever. These things are totally entertaining. There are real scientific advances coming out of even large language models, but other forms of AI. One of the criticisms is that it's really inefficient, right? That it's taking on the order of a gigawatt, some number of gigawatts to train a large language model. And one thing we think we know from biology is that brains have evolved to be far more energetically efficient, right? So the human brain is working at the rate of like 20 watts, right? Which is a pretty efficient light bulb. And your brain does a whole lot more than a light bulb. It's really astounding, right? But if you look at how much energy it took to train a brain to, say, a 20-year-old's year of amount of knowledge, it's only a few orders of magnitude less than it took to train something like ChatGPT. So yes, I think we should expect that these models can become more efficient, that they can learn from biology how to be more efficient. I actually think in the long run, there will be approaches that make these models far more efficient than the human brain is. Right? We look at calculating large numbers like matrix math and those sorts of things. Right? Computers are in some sense much more efficient at that. It's when we get to writing sonnets and things like that, it appears to be much less efficient. It is less efficient, but I think that when we look at the substrate, I feel like there's actually room for AI to become not just as efficient as biology, but more efficient. I think that's an area that should have a tremendous amount of research. And that efficiency came from a constraint, right? You had to acquire that energy from the landscape to feed yourself, to keep your brain alive. Evolutionarily, that it's a good deal, but again, it's not free. And thinking about putting constraints on these large language models, like the DeepSeek, right? The Chinese model, the DeepSeek model that came out and was far more efficient than other models because it built upon them. I think there's room for AI models because they are building upon the accumulated human knowledge. There's room for them to be much more efficient. They don't have to rediscover these things, right? They're essentially mimicking the patterns that we've identified. So I think that energetic efficiency of these systems. Both can learn from biology and leverage biology to potentially become much more efficient. And it would behoove us to spend some research energy on that.
Yeah, or part of the $1 billion that I just allocated to you.
You're spending that $1 billion very quickly.
Whether we talk about those LLMs or the immune system, and I know very little about it, but it seems that indeed you have some randomness that may actually derail the scaling laws, a new architecture, a new virus. I know nothing about the immune system, but you do see that some people are incredibly resistant. How is it possible that this person who's been drinking for 60 years is still alive? And on the other end, when you have someone unfortunately passing away, often you hear people saying, I just saw him last week and he was fine. So it seems that he could collapse in a very rapid way as well. Now, you are giving me so many research ideas, which is, for me, on the receiving end, definitely positive. How is it for you? So looking back at your academic career, doing research in biology and computer science and social systems, is it a path that first you enjoyed? I would assume probably yes, but would you do it again? And would you advise young researchers to follow such a interdisciplinary path?
So, fantastic question. Yes, I enjoyed it immensely. I still enjoy it. And yes, I would do it again. I don't know that I could recreate the path. There was a lot of randomness in my path. I followed the randomness. Maybe that's why I appreciate it so much in the ants. I'm too distracted by random events that lead to, hey, this is an interesting new place to take what I've learned and take it in a new direction. Is it the most productive way to have a career? Almost certainly not. People, I think, are probably more productive by following the paths that have been laid down by others. But it's far more interesting, I think, to be able to see these connections among different systems. So I absolutely... Let me give you a more nuanced answer. Yes, I would advise young students, young researchers to follow this path. In practice, though, I often didn't. For some of my earlier students, sometimes we would go down these paths, but there was always this idea, you really need to get a strong knowledge in your core discipline, whether it's computer science or biology. And because, again, you're going to need a job, right? You're going to need somebody to hire you, and there's going to be a committee in some department, and you're going to have to convince those people that you are one of them. And there is a tension there. I think there's a tendency to want to be more conservative for some of your students for their own sake, for the sake of their own careers. Now I'm much more with age. I feel like, let me tell you what you're in for if you pursue this path. But this is the path that I can help you pursue that I think is interesting. The excitement of finding commonalities across disciplines. It's thrilling. You've recently spent time at the Santa Fe Institute and just observing it yourself, observing it in other groups of people who can find these connections among really disparate disciplines. One, it's fun. It's intellectually I think, just so engaging. But tremendous progress has been made, right? And so I think this is maybe one of those ways. The Santa Fe Institute maybe is one of the examples of an organization that sort of goes off in a different direction, many different directions. And that's important. And maybe we need other models, other institutes that study things in different ways, but not in the standard way that university departments, for example, would study things. So I would absolutely encourage not just curious young researchers, but curious older researchers, curious institutions that have the ability to pivot and explore across the boundaries of disciplines and ways that people have thought in the past.
Yeah, I'm not sure how easy it would be to recreate something like the Santa Fe Institute from scratch, right? So to design it in a way to be sure that it will scale to what SFI is today, because you have people coming from many disciplines, but the key ingredient, at least from what I could get, is that they are interested in others for real. Because otherwise, you may have all the disciplines in the world you want, it will do nothing to build knowledge and new research.
Yeah, I think that's true, but I don't think at its roots, the Santa Fe Institute was designed to be scalable, right? It was designed to bring together people who had interests and insights across disciplines, and they built it from there. And I think it would be fine to have many such institutions with different sort of philosophies of that, to give that a try. And many of them wouldn't scale and many of them would fail. But again, we shouldn't be so afraid of failure, just like the ant that doesn't find any food. Trying different approaches to this, I think that should be one of the lessons that people take away from the success of the science of complexity. He's thinking differently, thinking about different ways to have individuals with different knowledge interact. Many of them will fail, and that's fine. It's the journey, not the destination sort of an approach. And some few of them will succeed and have real, I think, important scientific impact.
Yeah. What I meant to say is that if you were to design something with the ambition of scale, this may actually be the recipe for failure. So maybe
it could be.
Yeah.
Yeah.
Anyway, something to keep on exploring, but I must say that your path is incredibly stimulating and inspiring. So thank you so very much for everything you've done and for everything you will do in the future with the $1 billion I just awarded you. I'm very much looking forward to your research. I very much enjoy our discussion indeed at the Santa Fe just a couple of weeks ago. So I look forward to keeping in touch with you. So thank you so very much for coming on the podcast. It was great to have you here. I hope to see you soon. And to everyone out there, take care of yourself. And if you can, someone else too. Bye-bye.